Right, grade 12, let's have a look at theorem 7. We're revising the grade 11 theorems. And in theorem 7, what does it say? If you've got a center there, what can we do? In other words, the radius goes down and it meets the tangent ABC. Remember, what is a tangent? It's a line that touches the circle at one point only. And what do we know? That the tangent is perpendicular to the radius. The tangent is perpendicular to the radius at that point of contact there. Also, if you look at the theorem where you've got if you take a point outside the circle and you've got a tangent AB there, and you've got a tangent AC. Okay, now what do we know? Well, if we look at the length of AB and the length of AC, they are exactly the same. Okay, and because the radius is perpendicular to the tangent, look at that. We've got a cyclic quad here. B1 plus C1, look at that. B1 plus C1 is equal to 180 degrees. You add that, so that's a cyclic quad, and we've got, in fact, if you think about it, we've actually got a kite there. If you join that there, we've got a kite. The radii are equal, but the lengths of those tangents from A to B and A to C are equal in length. This is the concept of tangents from the same point outside the circle. Okay, so that's important. Now, the other important theorem is what we call the tan chord theorem. Okay, how does the tan chord theorem work? If you have a look at this, this is so important. I'm going to use some color here. If you look at this, if you take the tangent BC, alright, there's the tangent BC, that's a tangent. Okay, now what do we know? This is a tangent, this is a chord. Okay, so there's your tangent and there's your chord. The angle between the tangent and chord, now look at this, if you go angle between tangent and chord is the angle in the opposite segment there. Angle between tangent and chord is equal to the angle in the alternate segment. So we know that B2 is equal to E. If you look at something else, if that's AB is your tangent, then what do we know? Angle between the tangent and the chord. There we go. The chord is EB. And what a pleasure. The angle between the tangent and the chord is equal to the angle in the alternate segment, so B1 is equal to D. This is called the tan chord theorem. Okay, so be very careful, and it might vary a bit. You might have various different kinds of situations, and it is so important that you be able to look to master this tan chord theorem. It's so important because when you do matric geometry, you're going to need all these theorems. Okay, so let's focus a little bit more on this tan chord theorem. Okay, have a look at this one. If you take this example, for example, look at this. You've got, okay, we'll start off with BC. Okay, there's BC. That's your tangent. Okay, that's your tangent. And what is the chord? From the tangent, we go to the chord. Very important stuff, this. There we go. There's your chord. Okay, so there's your tangent. There's your chord. So the angle between the tangent and the chord is the angle in the opposite segment. So obviously, E and B2 would be equal. And likewise, if you have a look at this, if this was your tangent, now careful with this one. There's a tangent, there's a chord. Okay, now careful. The angle between the tangent and the chord is equal to the angle in the alternate segment. D is equal to B1. That's called, and all of this is referred to as your tan chord theorem. So be very careful. Remember this now. It's so important. If you've got a circle and you've got a tangent to the circle like that, there's the tangent, there's the chord. So you go up from the tangent to the chord and you follow and you go down towards the alternate segment. So that angle there equals this one here. The tan chord theorem, or this, is equal to that angle between tangent and chord. And by the way, what's very important with this is that sometimes they'll give you a little triangle like this, and they give you a line. Okay, and then they call this A, B, and C. And let's call that D and E. And they'll say, prove that that the CDE or DCE is a tangent to an imaginary circle that's going through A, B, and C. You want to prove that. So what do you have to prove? If you can prove that C1 is equal to angle B, the angle outside there is equal to the angle in the alternate segment, then automatically the tan chord theorem kicks in, and there would have to be a circle drawn around there. That is so critical.